Hello everybody, my name is Assoc.Prof.Dr. YILMAZ from Çukurova University, Adana, Turkey, and welcome to my lecture. Today I'm going to be talking about the fundamentals of internal combustion engines, the working principle of 4-stroke petrol engine, 2-stroke petrol engine, and 4-stroke diesel engines. And I will also show you some videos about the working principle of these engines. As you know, internal combustion engines are the hearts of the vehicles, the power generator that directly delivers the power to the wheels via power transmission systems. So it's very crucial to learn about these hearts of the vehicles. So in the first part of our lecture, the working principle of a 4-stroke engine I will explain. As you can see, in the first stroke is called the intake stroke. In the intake stroke, the piston moves downwards, and while the piston is moving downwards, the intake valve opens, and the fresh air or air-fuel mixture, fresh air-fuel mixture will be introduced into the combustion chamber. And in the second stroke, as you can see from the slide, the compression stroke. In the compression stroke, the intake and exhaust valves are both closed, and the air-fuel mixture, or just the air, fresh air, is trapped into the combustion chamber. As the piston moves upwards, the air-fuel mixture, or just the air, is being compressed to very high temperatures and pressure values. So in this third stroke, we call this power stroke. When the air-fuel mixture is compressed to very high pressure and temperature values, and there's a spark plug in petrol engines that when the spark ignites, there will be a little spark at about average of 50,000 volts, and this spark will ignite the compressed air-fuel mixture with a very severe combustion. When the combustion occurs, there will be a very big explosion, and with that explosion, a very huge power or huge force, downward force, will push the piston back to downwards. So this is the power stroke. This is the main stroke that the engine is producing the power. So in the third stroke, we have some residual gases we call exhaust gases, and we call this stroke as exhaust stroke. These residual gases should be expelled from the combustion chamber via exhaust valves. So in the exhaust stroke, the exhaust valves will open, and the exhaust gases will be expelled, will be scavenged through the exhaust pipe, exhaust manifold and exhaust pipe. So this is the main working principle of a 4-stroke petrol engine. And also we have some videos that is explaining the working principle of this petrol engine, 3D animations, and I think this will facilitate the understanding of the working principle. Can we open the video, the first video, please? Meanwhile, the petrol engines is also called as, or is also known as, spark ignition engines, because we use spark plug as ignition source. And this video is going to show the working principle of 4-stroke petrol engine. As you can see, there are a lot of moving parts in the engine. There are valves, intake and exhaust valves, and there are pistons, connecting rods, crankshaft. As you can see, the movement of the piston is linear, and this linear movement is converted to pendulum movement, in connecting rod, and this pendulum movement is converted to rotational movement in crankshaft. As you can see, the pistons, this is a 4-stroke, 4-piston, 4-cylinder engine, and there are valves, as I mentioned before. One sequence is intake valves and the other sequence is exhaust valves, and these are the names of some parts. The flame on the pistons depicts the power stroke in that piston, in that cylinder. As you can see, the sequence of this engine is 1-3 and 2-4. Intake, compression, power, and exhaust strokes. And the timing of the valves are precisely controlled by the trigger chain or trigger belt. It depends on the vehicle, it depends on the engine design. It could be a chain or it could be a belt. This is just one part, just one cylinder, one piston of the engine. We have a spark plug, as I mentioned before. It produces a spark to ignite all the fuel. This is the very fast process of the engine. In the intake stroke, in slow motion, the intake valve is opened and the fresh air or air-fuel mixture is being introduced into the combustion chamber. And now, at the end of the intake stroke, the valves are closed and the compression stroke begins. As you can see, as the piston moves upwards, the air-fuel mixture in the combustion chamber reaches high temperature and pressure values. And when the spark ignites, there will be a big explosion that pushes the piston downwards. This is called the power stroke. And at the end of the power stroke, we have some residual gases or exhaust gases, and these exhaust gases should be scavenged through the exhaust valves. This is the fast process of the 4-stroke internal combustion engine, spark ignition engine. It's a petrol engine, as I mentioned before. In the intake stroke, the mixture could be just a fresh air or air-fuel mixture. It depends on the technology of the vehicle. If it's a gasoline direct injection engine, in the intake stroke, you just take a fresh air into the combustion chamber. If it's a premixed combustion, premixed injection, or port fuel injection engine, for example, or is it carbureted engine, then air-fuel mixture will be introduced into the combustion chamber at the intake stroke. And this is the firing order, as you can see, 1, 3, 4, 2. And this is the end of the first video. And of course, this process is occurring in very small time, in milliseconds. We are talking about milliseconds. And the second video is the working principle of a 4-stroke diesel engine. The main principle is the same, but the fuel supply or ignition source is a little bit different from spark ignition engines or petrol engines. This is the 4-stroke diesel engine. We have no spark plugs to ignite the fuel in diesel engines. We have just fuel injectors. The fuel is directly injected into the combustion chamber. And this is our piston, and there are some rings, as you can see, around the piston. The piston rings are generally to prevent the leakage from the combustion chamber to the oil sump, or the oil leakage from the oil sump to the combustion chamber. As you can see, there are 3 movements here. The piston moves upwards and downwards. It's called linear movement. And our connecting rod, which connects the piston to the crankshaft, moves like a pendulum, and the crankshaft moves in rotation. The intake valves open as you can see, the fresh air is charged into the combustion chamber. This is called suction stroke or intake stroke. They are basically the same thing. And this is the compression stroke. As you compress the air in the combustion chamber, the temperature and pressure will rise very dramatically. And considering that the compression ratio of the diesel engines are too high, the temperature and pressure inside the combustion chamber is too high too. And we spray fuel onto this high temperature and pressure air, and there will be a big explosion, self-ignition. This is called self-ignition. As you can see, we used no spark ignition here. The air-fuel mixture is combusted by itself. But to make the self-combustion, we need to compress the air to very high pressure and temperatures, and we need to spray the fuel in very, very high pressures. In current diesel engines, in new technology diesel engines, the last era common rail engines, the injection pressure is about 3,000 bars. It's a very, 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 very high pressure. And the more the fuel pressure is, the more efficient the engine is. And the head of the piston is called piston bowel. The shape of the geometry of this bowel is crucial to make a good mixture in the combustion chamber, to make a necessary turbulent flows, or swirls or tumbles. And also you can see the trigger belt or trigger chain system that makes the timing of the intake and exhaust valves. The opening and closing time of intake and exhaust valves are so crucial for a smooth engine operation. If the valve, for example, intake valve closes before it should be, then there will be maybe knocking problems in the engine, or if the exhaust valve opens before it should be, so there will be other problems. Maybe the combustion efficiency will decrease. So the timing of the opening and closing of valves are so crucial. There are several technologies about these valves, variable valve timing, for example. The opening time or closing time of the valves are adjusted according to the engine load, and more efficient engines can be achieved. This is the pressure variation in the combustion chamber versus time. The sequence of the engine is written under the video. This sequence can be different from engine to engine. It totally depends on the engine design. And we have a flywheel here. Flywheel is a very heavy part of the engine that balances some dynamic fluctuations occurring in the crankshaft, because crankshaft is a very high rotational movement part, so there are always vibrations and inertias, so those vibrations or inertias should be balanced by a very heavy part that's called flywheel. Also, the flywheel is used for in the first startup of the engine. The starter will give the energy through the flywheel at the first moment when you start the engine. And also the flywheel carries the clutch system on itself. And we can move on to the next video. So, we talked about four-stroke diesel and four-stroke petrol engines. And this video is going to tell us this two-stroke petrol engine. Two-stroke petrol engines are generally used in small applications just like go-karts or lawnmowers or petrol engine saws to cut the trunk of the tree, for example. And this is the two-stroke engine operation. As you can see, there are no valves in here. There are no valves. There are just ports. The green fluid is the fresh air-fuel mixture. As you can see, the piston opens the intake port and fresh air-fuel mixtures is introduced into the combustion chamber. At the time of intake stroke, also there will be an exhaust stroke. Or at the time of compression stroke, as you can see, the fresh air-fuel mixture will be charged into the crank part or the system, not oil sump. There is no oil sump in two-stroke petrol engines. There is no other oil system or cooling system. Generally, these engines are cooled by air. They are air-cooled engines. As you can see, intake, compressed, and combust are occurring at the same time. And while expanding, the air-fuel mixture, fresh air-fuel mixture is introduced into the combustion chamber. The exhaust will be expelled at the same time. As you can see, as the piston moves upwards, there will be a suction. There will be a vacuum beneath the piston, and the air-fuel mixture will be charged in that crankcase. And when the piston opens the intake port, the air-fuel mixture will be introduced into the combustion chamber. The piston will go upwards and compress the air-fuel mixture. When the spark ignites, there will be a big explosion pushing the piston downwards, and the exhaust gases will be expelled through the exhaust ports. As you pay attention, I'm not saying valves in two-stroke petrol engines. I'm talking about ports here. So we can say that in four-stroke engines, in one cycle, intake, compression, power, and exhaust strokes. This is not the video that I have. This is irrelevant. In four-stroke engines, all the strokes are occurring at their own time, separately. They are occurring separately. But in two-stroke engine, intake and exhaust, combustion and compression are occurring at the same time. So in four-stroke engines, in one cycle, the crankshaft rotates two complete movements. It means to 720 degrees of angle. And in two-stroke engines, in one cycle, the crankshaft rotates just one complete. So it means that 360 degrees. In theory, the RPM, revolution per minute, of two-stroke engine is 2 times of a four-stroke engine. But there are also a lot of drawbacks about these two-stroke petrol engines. Just like they are very simple, this is an advantage, but the fresh air mixture and the residual exhaust gases are mixing together, so this decreases the combustion efficiency, and if the combustion efficiency reduces, so the thermal efficiency and the power, the torque the engine will deliver will be very reduced. So the efficiency, in general, the efficiency of two-stroke petrol engines are much lower than the four-stroke engines. So they are not suitable, they're not appropriate for transportation we cannot use those two-stroke spark ignition or petrol engines for passenger cars or buses or other transportation vehicles. But we can use them in small applications, as I mentioned before, because they are simple, they are cheap, and they are light. But four-stroke engines are much more complex. They have a lubrication system, they have cooling system, radiators, water pumps, or oil pumps, and the canals or other pipes maybe to transport the fuel, to transport the oil or cooler to the other parts of the engine. So in the end, we can say that the four-stroke engine is much more efficient than two-stroke engines. I'm talking about petrol engines. So four-stroke engine is suitable for transportation, but two-stroke engine is not. There are also two-stroke diesel engines. Two-stroke diesel engines are not common engines, but they are generally used in very big ships, for example, container ships or big cruise ships, maybe, because two-stroke diesel engines are much more efficient for those kind of engines, because they are very huge engines and the pressure, the fuel pressure should not be lost especially in the power stroke. So in such a big size engine, the pressure loss is inevitable in fuels. But you need to transport, or you need to move the maybe thousands of tons of this ship on the water. So you cannot consider the big pressure loss in fuels in those kinds of engines are not acceptable. So two-stroke diesel engines are generally used in very, very big applications, just like transportation ships, container ships, or cruise ships. Okay, let's proceed. And there are also some terms about the internal combustion engines. As you can see here in the graph, in the figure, there are some terms like top dead center, bottom dead center, stroke, or I mentioned about spark plug or fuel injector. And top dead center means the upper limit that piston can reach, the upper limit, the piston, the theoretical limit. Okay, in real life, in real engine operation, the piston never reaches the top dead center. But in theory, we accept that the piston reaches the top dead center. This is the last point, maximum point that it can reach. And the bottom dead center is the minimum point that the piston can reach. This is called the bottom dead center. The volume between the top dead center and the bottom dead center is called stroke volume, where the piston sweeps. Okay, so the clearance volume is the volume between the top dead center and head of the piston, or head of the cylinder, let's say. This is called the clearance volume. The clearance volume is an important parameter because it directly defines the compression ratio of the engine. So, speaking of compression ratio, let's explain this term. Compression ratio, the first term here, is the ability of the engine to compress a unit of air-fuel mixture or air to small volume. If the compression ratio is very high, if a compression ratio of an engine is very high, then this engine is capable of compress the air or air-fuel mixture to a very small volume, a very big volume of air or air-fuel mixture to very small volume. In diesel engines, generally the compression ratio is to be much more higher than the petrol engines, because in compression ignition engines or diesel engines, as I mentioned in the video, if you recall the working principle of the diesel engine, we need to compress the air to very high temperature and pressures. So in order to do that, we need a very high compression ratio values. The engine, the piston, should compress the air to very small volumes. So the compression ratio of diesel engines are generally much more than the compression ratio of petrol engines. But in petrol engines, if the compression ratio is too high, then the air-fuel mixture is prone to ignite by itself before the spark plug ignites. This is an unwanted thing. We don't want this. We just want the combustion will occur after the spark plug ignites. But before the spark plug ignites, if the air-fuel mixture is self-ignited in petrol engine, this is not the thing that we want. We call this engine knock. This is called engine knock. It will make some vibrations, it will make some other dynamic problems in the engine, and at the end of this knocking problem, if we cannot overcome this knocking problem, the engine fail will result in engine fail. So knocking is a very important problem in engines, also in diesel engines. So in spark ignition engines, we don't want the air-fuel mixture to be ignited before the spark plug ignites. We don't want very advanced ignition. But in diesel engines, the situation is just vice versa. If the ignition delay, we call it ignition delay, when we spray the fuel onto the high temperature and pressure air in diesel engines, we want that the combustion occur at the same time, but in real life, in real engine operation, it's not occurring at the same time. When we spray the fuel onto the air in diesel engines, hot and high pressure air in the diesel engines, there will be a very short ignition delay time. And after that time, the ignition will occur and the combustion will occur, and the engine can produce the power. So if the ignition delay time is too long, then the engine will show some knocking problems in diesel engines. So we are trying to shorten that ignition delay time in diesel engines. So if you summarize the ignition delays or self-ignitions, in spark ignition engines, the air-fuel mixture should not be ignited before the spark plug is in operation. In diesel engines, the ignition delay time should be as short as possible to overcome or to prevent the engine knocking problem. So the compression ratio, if the compression ratio, we can link this subject to the compression ratio. If the compression ratio of a spark ignition engine is too high, just like diesel engine, then self-ignition problems will occur. So we cannot make a very high compression ratio spark ignition engine. It varies between 8 to 12 for petrol engines. 8 to 12. What does 8 or 12 or 10 compression ratio mean? It means that if we say the compression ratio of this engine is 10 to 1, it means that the 10 units of air-fuel mixture can be compressed to 1 unit of air-fuel mixture. This engine is capable of doing that. Okay, so compression ratio is directly related to the thermal efficiency of the engine. So it's a very important parameter. And how do we calculate compression ratio? Compression ratio, as I mentioned before, is the ability of engine to compress the air to 1 unit of volume maybe. So it means that the compression ratio is equal to total volume of cylinder over clearance volume. because we assume that we compress all the air or air-fuel mixture to the clearance volume. So if we denote the clearance volume as VC and stroke volume is the volume between top dead center and bottom dead center, as you can recall, and clearance volume plus stroke volume is the total cylinder volume over clearance volume. And if we arrange the equation, it's Vs over Vc plus 1. This means that the compression ratio of an engine is always bigger than 1. Okay, as I said before, it's 8 to 12 for petrol engines, and it's 15 to 22 or 24 for diesel engines. And we have another term that's very important for engine characteristics. Is called thermal efficiency. Thermal efficiency is the efficiency means what we pay and what we take against that payment. Okay, for example, thermal efficiency is the work done by the engine, because we put fuel to engine to make it work. Okay, we need work from that engine. That's why we put fuel. So we put fuel, but how much percent of that fuel is converted to the work in the piston, for example? This is called thermal efficiency. Currently, vehicles for spark ignition engines or petrol engines, new technology petrol engines, the thermal efficiency is about maybe 35 or 40%. This means that the 40% of the fuel energy is converted to energy in the piston, work in the piston. The other 60%, the most of the fuel energy is released heat to the atmosphere, especially from the exhaust system. So we literally lose most of the fuel energy in the engines. In diesel engines, the thermal efficiency currently, I'm talking about the current new technology diesel engines, it's about 55, maybe 60%. It's much more efficient than petrol engines, because diesel engines have higher compression ratios, which is directly related to the thermal efficiency of the engine, as I mentioned before. And there are also performance parameters for the engines. There is effective power. Effective power means the power produced in the crankshaft. Because you make the combustion occurs in the combustion chamber in the cylinder. There will be a very big energy, and some of this energy will be used to push the piston downwards, and most of it will be lost as heat into the atmosphere. And there are also connecting rods and crankshaft. There are also some frictions, some dynamic parts here. So there will be some losses there, mechanical losses. And at the end, we have the power at the crankshaft. This power is called effective power, PE. We denote it as PE. And this is the important part, because the power in the crankshaft is important, not the power in the piston. Crankshaft, then the power is delivered to the transmission system. From the transmission systems, power transmission systems, in the end, we deliver the power to the wheels. And the most important power that is the wheel power, of course, because in the wheels are moving the vehicle, so the wheel power is the most important thing. But of course it depends on the power delivered by the engine and the crankshaft. So the power in the crankshaft can be calculated with this equation, 2 pi nt over 60,000. And this 2 2 pi means 1 rotation of crankshaft in radian. N means the engine RPM, revolution per minute, engine speed, the crankshaft's speed. Okay, the value that we see on the dashboard. T is the torque or the moment. We call it as moment. It's the ability of the engine to make the necessary rotational moment. Okay, it's a very important parameter for engine performance, and we divide it by 60,000. It's just for converting the units. Okay, and in the end, we find the crank power in kilowatts, not in horsepower. If you want to convert the kilowatts into horsepower, then we should multiply it by 1.36 or 1.4 maybe. Okay. And this is an example, a very simple example. This is a dynograph of an engine. Dynograph means we calculate or we determine the performance of an engine with dynamometers. The dynamometers have some cylinders, and the driven wheels are located on that cylinders, and we load the engine. Those dynamometer cylinders are used to load the engine, because if you load the engine will produce power. If the engine is working in idle or idling, there will be no power. So we need to load the engine. We need to force the engine to make it deliver, to make it produce power. So in the dynamometers, we are doing the loading process. And as you can see, the vertical axis shows the power that the engine is producing at the time of dynamometer tests. And the horizontal line shows the engine speed, the value that we see on the dashboard. Okay. And as you can see, the power tends to increase until about 5,000 RPMs, as you can see, because the air-fuel mixture is developing and the engine is prone to produce more power. But after about 5,000 RPMs, the engine power is prone to decrease, as you can see. This is because in very high speeds, the intake valves are closing and opening very fast, because the intake valves are adjusted, the opening and intake timing is adjusted by the camshaft, as you can recall. And the camshaft is driven by the trigger system, and the trigger system is driven by the crankshaft. So if the crankshaft rotates very fast, then the camshaft will rotate very fast, and the valves will open and close very fast. So there will be no enough time, there will be no adequate time for air, for fresh air or air-fuel mixture to be introduced into the combustion chamber. So the engine cannot breathe very comfortably. So the engine then will be prone to produce less power after a certain RPMs. So we can say that in the end, we can say that as the crankshaft rotation speed is higher, if it's the higher the crankshaft rotation, the more power will be there. No, it's wrong. Until some engine RPM or RPM range, the power will increase, and it's also valid for torque. This is just a power graph, but it's also valid for torque, because the torque and power is directly proportional to each other, as you can recall from the effective power formula. And in the first question, it asks that find the torque at maximum power. We are looking at the graph, and it asks us the torque at maximum power. And we know the maximum power RPM from the graph. It's about 5,000 RPMs because the power reaches its maximum at about maybe 110 horsepower at 5,000 RPMs. So if we pay attention, the power axis is given in horsepower, but this power equation is in kilowatts. So we need to convert the horsepower to kilowatts in the first place. So the maximum power is about 110 horsepower, and it's equal to 81 kilowatts. Then we can use this formula. Okay. We shouldn't forget to convert the horsepower to kilowatts. And if we put the values in the equation, power equation, 81 is equal to 2 pi 5,000 or 5,200 maybe. It's not an precise thing in that graph. And it's asking us the torque value at the maximum power, and we put T over 60,000. And if we calculate it, it's about 150 Newton meters. It means that this is not the maximum torque the engine is delivering. We should pay attention to here. This is not the maximum torque. This is the torque value when the engine is giving the maximum power. Okay? We understand that from the first question. At about 5,000 or 5,200 RPM, so engine speed, the engine is giving us the torque of 150 Newton meters. But this is not the maximum torque. Okay? And in the question B, it asks find the torque and power at 4,000 RPMs. And we can see it on the graph. At 4,000 RPMs, if we draw a perpendicular to the graph and intersect it with the horizontal line, the power at 4,000 RPMs is about 100 horsepower. But we need to convert it to kilowatts to use this effective power formula, as you can recall. And it's, if we divide 100 by 1.36, it's about 73.5 kilowatts. And we can directly read it from the graph. And it asks us the torque value also. So we can find torque from this equation. If we calculate the torque and if we put the values into the equation, substitute the values into the equations, and we can find 175 Newton meters. It means that at 4,000 RPMs or engine speed, the engine will produce about 175 Newton meters of torque and 100 horsepower or 73.5 kilowatts of engine power. And this is the pressure volume graph of a 4-stroke SI engine. SI engine means spark ignition engine, as you can recall, and we also call it as petrol engine. And diesel engines are also known as compression ignition engines because we compress the air and we spray fuel onto that high pressure and high temperature air, as you can recall. And this is the real pressure cylinder volume graph of a real world engine, okay, not an ideal engine. In the intake stroke, as you can remember, in the intake stroke, the piston moves downwards, and the volume pressure in the combustion chamber at the time of the intake stroke is lower than the atmospheric pressure. It should be, because there should be a vacuum. There should be a vacuum that the atmospheric pressure or atmosphere air should rush into the cylinder, because the flow is from high pressure to low pressure. So in the intake stroke, the pressure in the combustion chamber is lower than 1 atm. If we assume that the conditions are in normal conditions. In the sea level, 0 degrees Celsius air temperature, the atmospheric pressure is about 1 atm, as you know. And in the first star, intake valve opens. Intake valve opens. We introduce the air or air-fuel mixture into the combustion chamber, and in the second star, the right one, the intake valve closes. This is the end of the intake stroke. Now we have fresh air-fuel mixture or air in the combustion chamber. Then the compression stroke will begin, will commence. So the compression stroke begins. As you can see, the pressure is starting to rise, of course, because the compression stroke begins. It begins to rise, and in the red star, the spark ignites. The spark ignites, and the air-fuel mixture is combusted with a very high explosion, and the flame is spreading into the combustion chamber very fast. It's about, the average flame speed is about 20 or 25 meters per second. It depends on the engine operation, engine load, engine rev, RPM, but for an average small SI engine, it's about 20 or 25 meters per second, the flame velocities. And at the end of the compression stroke, the spark ignites and there will be a big explosion. And as you can see, the pressure value rises, it reaches its top at the end of the combustion, its top. And power stroke, the power will be produced and the piston will be pushed downwards. We have now residual gases in the combustion chamber. So the exhaust valves should open, and the exhaust valves open in the star, as you can see there. And the exhaust valves are scavenged through the exhaust valves or exhaust pipe, manifolds, pipes. And the cycle, after the exhaust cycle reaches the beginning point, and the other cycle begins. This is the pressure and cylinder volume graphic of one cycle, and this cycle also always repeats. The TC in the horizontal axis is top dead center, and BC is bottom dead center. As you can recall, it's the upper limits and lower limits of for the piston. And this is the intake and exhaust valve opening and closing characteristics graphics according to top dead center and bottom dead center. In the first graph, IVO means intake valve open. Intake valve open. When does it open? At the start of the intake stroke. So intake valve open just before the top dead center, as you can see. Intake valve, IVO, intake valve open, and the air fuel mixture is being introduced into the combustion chamber, and after a very short while the exhaust valve closes from the previous cycle, and intake valve open until the bottom dead center, as you can see. And this range is called intake stroke. And after the intake stroke, the compression stroke begins. In the compression stroke, all valves should be closed, both intakes and exhaust. And in the compression stroke, as you can see, the pressure starts to rise, and at about top dead center, it reaches its maximum, as you can see. And the spark ignites and the power will be produced and the piston will be pushed downwards. And in the during the expansion, the exhaust valve opens, EVO, as you can see, because the exhaust gases should be expelled should be expelled through the exhaust system. The opening in a very short time, the intake valve and exhaust valves are open at the same time. This is called valve overlap. And another performance parameter is called BMEP. It's called brake mean effective pressure. It's a fixed pressure value. That means if we remove the combustion parts, combustion process, and if we substitute this combustion process with this pressure, it will do the same thing. It's a fixed pressure parameter, but it's very important for engine designs. As you can see, the BMEP, brake mean effective pressure, it's an average pressure in the combustion chamber, is dependent on brake power and displacement volume and the engine RPM. So it means that the produced power per displacement volume. We can explain like that. And there's also an example for BMEP. So we can solve it here. If we have time, we can solve it here. I think we have time. Okay. And in this example, a 4-stroke, 4-cylinder automatic spark ignition engine is being designed to provide a maximum brake torque of 550 Nm in the mid-speed range, about 3000 RPMs. And let's say it says 925 kilopascals is an appropriate value for BMEP at the maximum engine torque point. It means that when the engine is delivering the maximum torque, the average pressure in the combustion chamber is about 925 kilopascals. And in the second bullet, it says typical BMEP value at maximum power is 800 kilopascals. When the engine is delivering the maximum power, the mean effective pressure in the combustion chamber is about 800 kilopascals. And B is equal to L means the bore, the diameter of the piston, is equal to the length of the piston. It's called square engine. Currently, the most of the engines are square engines, especially spark ignition engines. The bore means diameter of the piston, and L is the length of the piston. If the diameter of the piston is equal to the length of the piston, it's called square engine. And in this example, it's a square engine. The maximum mean piston speed is 15 meters per second. Estimated required engine displacement, bore and stroke, and the maximum brake power the engine will deliver. In the first place, we have in the first paragraph, we have maximum brake torque, and we have also the RPM. The engine is delivering 150 Nm of maximum torque at 3000 RPMs. So we can calculate the power here from this equation. Because we have engine RPM, we have engine torque, so we can calculate the power. And if we calculate the power from here, PE is equal to 2 pi NT over 60,000. And PE is equal to 2 times pi is 314. And the engine RPM is about 3000. And the torque value is 150 over 60,000. If we do that calculation, I think it's about it's roughly, I think, 50 kilowatts. And 50 kilowatts, it's about if you multiply it with 1.4, it's about 70 horsepower. And in the first place, we calculated the engine power, and it says estimate the required engine displacement. Engine displacement means the volume of the cylinder. Engine displacement, volume of the cylinder. And we can also use this formula, BMEP formula, to find the engine displacement. It's 925 kilopascals. 925 is equal to PB. It says PB, and this PB is maximum engine torque point. At the maximum engine torque point, we found the power. It's about 50 kilowatts, as you can see. So we can substitute it over NR. NR is the rotational crankshaft in one cycle. This is 2 for 4-stroke engines, so we can multiply it with 2 over this, just for unit conversion, and VD over RPM. And we can find VD from here. This is the displacement volume. So we can calculate this displacement volume from this equation. Also, it asks us the bore and stroke. So if we find the displacement volume, as you can see, the displacement volume is equal to P bore square over 4 times L. This is the volume of a cylinder. The bore is the, as you can recall, the bore is the diameter of the piston, and L is the length of the piston. So the volume of the cylinder is calculated with this equation. So if we find that VD from that equation, and we substitute this here, and B is equal to L, as you can see there, we call this square engine. So we can write L, B, or B for L, and we can find B and L from there. So we can find the bore and stroke from that equation. And this is the end of my lecture. Thanks for listening. I hope my lecture would be very beneficial for the target group. Okay, thanks for listening. See you soon.